to uncertainty quantification in a symbolic of crystalline materials. So please check the floor with you.
Thank you. Hi everyone. So because probably most people don't really know me, I will briefly myself. So I'm a former PhD student of Christoph Schran, who was giving a talk on Monday. And my thesis, I worked on applied analysis and on the problem of atomistic models of fractures. So I'm a mathematician. And then after my PhD, I moved to Cardiff in Wales to do a postdoc, and that coincided with the pandemic, so it was a bit tricky. And the work I'll be discussing today is with Angela, Mihai, and Thomas Woolley from Cardiff. So Angela is an expert in continuum stochastic elasticity. So that's what I'll discuss. And then at the very end of this postdoc, I realized that this can be translated to sort of modern machine learning potentials. And so we had a few discussions with Genevieve late on last year about how to extend it, and hopefully we can proceed with it. But in the meantime, I found a job at Weymuth as a postdoc, and that's in an unrelated area. So the project with Genevieve is somewhat on hold, but we'll see how it goes. Yeah, so what's the motivation here? So actually, I would refer to the talk by Dallas on Tuesday, where he discussed the importance of the choice of prior in this Bayesian inference procedure. And I basically paraphrase his words here, saying that would there be a systematic way to form a meaningful prior for the parameters based on the physical constraints that are present in the system? And as I mentioned, Angela is an expert on the sort of continuum level description of these problems. So here, what I'll do is I start with an atomistic model with an interatomic potential, and I try to couple it to a corresponding continuum model and use the sort of fairly well-established theory. Actually, Angela is just about to publish a book about the topic, and see whether some of the insights can be translated to the atomistic setup. And in particular, the tool I used to connect the atomistic model to the continuum one is the so-called Khachik rule, which I'll discuss in a bit. And in particular, this work here is also related to Ian's work. So in Ian's posters, he uses maximum entropy principle to derive a prior based on certain constraints. And I, as a mathematician, I look at a toy model that you can go a bit deeper into that, and hopefully at some point we can sort of converge on a more applications-focused model. Yes, so in particular in the stochastic elasticity, there is a fairly well-established idea of using information theory to derive least biased prior distributions for model parameters. Okay, so because there's two, I'll stand here now. Okay, so what's the setup? We have some M atoms, and the configuration is capital R. And in particular, as I mentioned, I look at already at the level of interatomic potential description, and in particular, I have this body order expansion, and we truncated some N. And in particular, for my toy models, I disregard the one-body terms, and in particular, I really just consider two toy model cases. One is just pair potentials, and in particular, it's the Lennard-Jones potential. And then in the latter stages, I'll also briefly touch upon the case where I also include three-body terms, and it's a basic prototype machine learning potential in the APIP framework, which was developed by Cass, who has a talk just after me, Genevieve, Gabor, and Christoph, so everyone that's here at the workshop, conveniently. Okay, so just to continue, as was touched upon in the talk by Christoph on Monday, basically you can rewrite this in this sort of form. So you take any two atoms, you look at the difference, at the distance, at the difference of their positions, and you can actually rewrite it as a sort of in this site potential framework. And in particular, There are some invariances induced correspondences. So for instance, we can say that the two-body term just looks at the difference in the distance between them. And for three-body terms, for instance, we can say that they are distance-based, so then it's just the distance. But of course, you can also look at angle-based three-body representation. Yeah. And because I'd like to connect to continuum theory of elasticity, it's actually convenient to switch the notation, and hopefully I'll not lose you in the process. So I did some labeling and colors. So basically, because we're interested in crystalline materials, there will be some reference configuration R0, which is a Bravais lattice. For instance, you have a triangle lattice. And then instead of talking about configurations, we talk about deformation and displacement. So the full deformation is YU is induced by a displacement U. And in particular, normally we label the atoms by just, from 1 to J, 1 to M, capital M. Here we really talk about function where M is now just an atom in the lattice. And in particular, this notation with the differences, this can be sort of recast. It's just notation, but you have finite differences, and then you can gather them together to talk about the discrete gradient, which connects it to the continuum theory quite nicely. And so we can just as well write this energy in this form. So we sum over all the atoms, and we have this side potential, and then we look at this discrete gradient, and hopefully I made it clear that this is just equivalent to the previous representation. Yeah, and in particular here, it's a subtlety that I basically fix the interaction radius. So it's actually it's quite important here. Basically, I a priori say how many, it's not about introducing cutoffs, although, you can make it sort of equivalent, but I basically a priori choose the cutoff, and in principle, you can also think of it as having infinite interaction range, but it's just a subtlety. So that's not really relevant here. Okay, and so having this model, we basically have some physics induced constraints. And what are they? What is the sort of bottom line? So they are related to the lattice constant and the Cauchy-Born rule. So we do a Taylor expansion around the lattice. So that would be the displacement equal to 0. And in particular, we look at the first two variations. So here they are written. Hopefully the color helps you see what is what. And also bear in mind at this stage, V is just any interatomic potential. It can have as many parameters as you want. It can be a fancy machine learning one. It can be written in this way nonetheless. And from the sort of applied analysis point of view, when we look at these atomistic models, the typical assumptions we make is that the perfect lattice is a stable equilibrium. And so for that, you would have that the first variation 0 and that the Hessian is positive definite. And that's the mathsy way of writing it. But really, as far as the sort of UQ is concerned, this is perhaps too strict. So how about we try to relax it a little? So for instance, instead of looking at any displacement, let's say I just look at uniform displacements. So basically what the saying is that we just look at displacement that would sort of take your lattice and, for instance, shrink it a little or tilt it a little, but it's a uniform displacement. If that's the case, then this first variation ends up being like as this sum, and the second variation is this, and L and S, there's a formula for it, and in fact, when I cover examples later, it will be shown explicitly. So let's say we want to impose these conditions, but only in the class of uniform displacements. So in particular, to say that the perfect lattice is an equilibrium would be to say that these Li alpha are 0, and in particular, in a way, it's not really a constraint in the sense that hidden in all that is that the lattice that you consider has a lattice constant parameter, and basically for a given choice of the interatomic potential, there will be some L. So basically, this equation just determines the lattice constant. It's not a specific constraint. Okay, and so here comes the connection with the continuum theory. So the Cauchy-Born rule in our case tells you that if you have an atomistic model which is described by this interatomic potential V, the sort of consistent way of coupling of deriving a corresponding continuum model would be to define the strain energy function W of F via this formula, and in particular when we rescale, A is the matrix that defines the lattice. So for instance, if it's a square lattice, A is just identity, but L is the lattice constant. And in particular, in a way, you can already see why this is true, because basically, when you then Taylor expand the strain energy function and you end up with, in the regime of linearized elasticity, so this is the elasticity tensor, you end up with this nice connection. So these entries are actually exactly these SI alpha J beta. So that's in a nutshell why this is the way to define the corresponding continuum model. Okay, and so at this stage we can have a look at the theory of continuum stochastic elasticity and see what's there. So in particular, I look at the linearized elasticity. So in Taylor notation, you have the strain tensor, which is the displacement gradient in the symmetrized form, and the constitutive stress-strain relation is that you have your strain tensor and you do the tensor product with the elasticity tensor, and then the equilibrium configurations are obtained by solving these equations. And here's the Einstein summation notation is assumed. And so at this level of description, the elasticity tensor is our base object. And depending on the symmetry class that you consider, it can have between 2 to 21 independent entries. So in the fully isotropic case, it's just 2 entries. And in the fully anisotropic case, there will be 21 independent entries. And in particular, this 4th order tensor can be represented as a 6x6 matrix. And in particular, you can decompose it. So these MIs are just basis elements. And in particular, these parameters CI, you can gather them together as a vector C. And these are the basic parameters in your model at the level of continuum linear elasticity. And this paper here, which is basically our work is based on it, it looks at exactly this setup and considers all the different symmetry classes and uses maximum entropy principle to say what is this bottom line statistical dependence or statistical or probability distribution based on constraints that arise from symmetry, and also some very basic constraints that I will discuss now. So precisely, so they look at a pretty minimal set of constraints. So first of all, the mean value of the tensor is known. So you basically, that can be set to the sort of default parameters of your model. And then the elasticity tensor and its inverse both have finite second order moments. And this is claimed to be for physical consistency. And it makes sense. Except that in the way they actually so in the maximum entropy principle framework, they actually sort of introduce this log of the determinant. And so in fact, you end up in a situation where all the moments are finite. So it's a sufficient condition, but not the necessary one. Okay, but either way, the whole point is that all these constraints, and you can think of, for instance, for your application to, if you look at electronic structure calculations, you might have some different constraints, but what's quite important is that they are all written as expectations. So in particular, first n entries of f would just be the components, and then h would be the mean value that you know, and then the final one would be this function here, and the expectation of this function here is meant to be finite. That's how you phrase it, and then the final constraint is just that the normalization constraint, so that you end up with a probability distribution. And using the maximum entropy here, basically you arrive at a conclusion that the least informative prior on C looked as a single random variable, so it's the joint probability distribution, is given by this density here, and these lambdas are Lagrange multipliers related to the set of constraints. And in particular, the key point here is that because you phrase it as a log of the determinant, you will see that if you look at the determinant of the elasticity tensor, you study the separability of this function, because if you have separability, so additive decomposition, then if you plug that in here, you will see that you end up with the joint probability distribution decoupling into independent ones. So then you can establish that in a given symmetry class, you have certain parameters that are statistically independent. And as I said in this paper, which is, I really like it, they go through all symmetry classes and they arrive at conclusion like that certain moduli, even under these very mild constraints, should be statistically dependent in any model that you do, and so on. Yeah, so that's the detour to continuum elasticity, but we can now come back to our atomistic model. And the point, as I mentioned, now the elasticity tensor, these elements, the entries of the elasticity tensor are derived quantities. They are the possibly very nonlinear functions of the atomistic, of the interatomic potential. So really what we like to do is just mimic the approach. Our minimal set of constraints is that you know your default values of your interatomic potential. And then again, you say that Cauchy-Born elasticity tensor have finite order second moments. And in particular, we study the separability of this function here, which, as I said, is now a function of the parameters of the potential. Okay, and now I mentioned I'll discuss two examples. So first one is just Lennard-Jones potential. So the site potential V can just be decomposed into a pair potential. And in particular, here's the Lennard-Jones potential. And you will notice that purposefully, I put the second parameter in the denominator. Typically, it's introduced in the numerator. And I'll explain why that is, because it ends up being way more convenient. And so we just have two parameters. And generically, this Li that I derived a few slides ago for any pair potential will have this structure. And so if we want Li alpha to be 0, first of all, the off-diagonal entries will be 0 just by symmetries of the lattice. So you just look at the, not to discriminate against this part audience. So basically, so in this particular instance, when you do the calculations, it turns out that, as I said, this determines the lattice constant, and as you probably know, in the Lennard-Jones case, it's just a function of A2, and these two parameters, these two constants, beta and alpha, they can be calculated, and they depend on the interaction radius that you impose. And even in the infinite case, it will still converge to a specific value. And again, for pair potentials, you can do the algebra, do the calculations, and you see that generically we will have this form. And in particular, you will notice that because we impose that this is 0, then this part will actually go away. And so you might know that any pair potential will satisfy the Cauchy relations, and this is precisely why. So the Cauchy relations is a equality between some entries of the elasticity network. Yeah, so in our paper, and we actually look at, we try to apply it to sort of stochastic model, zero temperature stochastic model of fracture, because as I said, I work on fracture. We have this proposition, so if you have in-plane elasticity, so just 2D, and you work with the triangle lattice, then you can, under these constraints that I discussed, you can say that these two parameters, so the joint probability decouples like this, so you can say that they are statistically independent, and in fact, they both follow gamma distributions, and K1, K2, lambda 1, lambda 2 are Lagrange. So normalization constant can also be thought of as a Lagrange multiplier. And then tau levels controls the levels of fluctuations, and in particular, that's why I introduce alpha 2 as an inverse of what it typically is, because if you think of here, we have 1 over A2, then this is 2 tau, and so then tau would have to be between A half to 1, and then your sort of level of control over statistical fluctuations is limited, as long as you still want to stay in the regime where they are actually gamma distributed. So just for convenience, it's best to rephrase it that way. Okay, and really what connects my work in at least tangential way to this workshop is that we'd like to do it for modern machine learning interatomic potentials. So for a few weeks late last year, we discussed it with Genevieve. So I looked at their AKIP paper, and then the energy can be expressed like this. And let's say I only do 2 body terms and 3 body terms. And then you have your basis elements of some prescribed polynomial degree, and you can gather all your parameters. And in particular, again, using this equivalent formulation, you still have it like that. V2 is a pair potential. It's not a nonlinearity like in Lennard-Jones, it's just a polynomial. But here I wanted to point out that V3 can be expressed like this, especially for the zero displacement. And the point is that they introduce a change of variables to that reflects the symmetries in the problem. So this function phi actually is phi star, where this is the function that respects the symmetries. And so at this point, these are our basis elements, and these are our the parameters that are related to the third body order. And okay, well, we have that. Let's do these calculations again and hear what comes up. So I used computer algebra software Sage Math. So this would be a certain entry of the elasticity tensor. But here, the equation for the lattice constant, so the sort of equilibrium level constraint, you will see that this is actually, so you can take L out and you end up with a quadratic equation. And so you really want this quadratic equation to have a positive solution that gives you a lattice constant. So you can look at the quadratic formula and tell you that, in fact, you can clearly see that they have to be statistically dependent, because you can't just vary any as you like, because then you can end up with no solution, for instance. Yeah, so really just to sum up, because I think I'm running out of time, perhaps there is a way forward, and perhaps there is, you basically knowing this framework, you can build a framework around it. So, you can have a specific formulation of constraints, because it's a bit of like a it's more art than science, I suppose, like modeling choices, specific change of variables, specific basis elements, and in particular, Christoph touched upon that you can think of reintroducing the physically motivated nonlinearities. perhaps if you combine it all, you end up with something that is tractable and it's not a mess, basically, but I'm not sure. And also, at the end of the day, perhaps it's not worth it because ultimately, like, you do all this work, you have your prior and you do the Bayesian inference, and perhaps you end up with, it's not much different. But more generally, that is perhaps helpful for everyone here. So Dallas mentioned that we need to recast our constraint in some sort of probabilistic language. So this is, in principle, it gives you a way of translating any sort of constraints that you have into a probabilistic language. And in particular, I touched upon it, if you can recast it as an expectation, then the framework is easier to use. But again, as you have seen, pretty much, beyond simplest cases, toy models for mathematicians, it probably gets intractably messy. But in any case, perhaps, yeah, basically the first part here is something that we'd like to work on and see if we can push it on just a little bit further. And with that, and final thing is, next year, Angela, my boss from Cardiff, she's organizing a program at the Newton Institute in Cambridge. It's more on the sort of continuum level, but she would like to add some sort of component of atomistic modeling into it, and I think I'll be mildly involved. So if anyone here would like to get involved, please get in touch with me. And they are still at the level of sort of deciding what will be in the program specifically, but if anyone is interested, please let me know. And with that, I'd like to thank you for your attention, and it's been a wonderful workshop. And thank you, and I'm happy to answer any questions.
Time for questions. Maybe start. You make an assumption, so that's the Khachik board assumption.
Yeah.
So what is the error propagation that you get when you do this approximation? Is Khachik bound relevant all the time, or often, or not often? What's the...
Well, basically, instead of Khachik bound, we should probably, ideally, we would like to work with these. And really, it's, as far as I understand it, it's a pretty hard problem. So for instance, you have a result that if you have this lattice stability, then you will get that, you will have the stability of the Hessian of your W, but probably it's right, you should know it in fine detail if you really want to apply it in this sort of error control way.
But in practice, do you know how important? Yeah.
Well, I mean, the Khachik bound rule is known to be applicable if you only slightly deviate from the lattice structure. So there's this famous paper by Frieseke and Heil that discusses that if your displacement goes away too much from the reference lattice, then you can sort of say that it doesn't apply. But really, the point is that if you go away too much, then because you fix the interaction range, and if you then pull it apart, then the interaction range is not really relevant because. So that's why it doesn't work. So then you should probably relabel or change your interaction, and then it should still be applicable. But so you really should work with it when you have a specific crystalline structure in mind, and you just look at minor deviations from it.
So here you're using like quantitative information, specific data streams that require some aspects, such as that overall amount of constants.
Yeah.
So often when we talk about priors, what we really want to encode is qualitative, like the fact that, say, atoms are reported at short distances. So do you have like some thoughts on how this sort of thing would be done in such a rigorous
I don't. It's the honest answer. That's why really like one of the, so touching upon like throwing out open problems into community. So when you look, say, at the lower level theories like electronic structure, like the question here is, so these constraints come from a higher level theory, but the question is what sort of constraints you can feed into it that come, say, from electronic structure theory. So I guess that would sort of encode that they are, you know, for instance, two atoms can come too close together. But I don't have any insight.
I think the most basic quantitative thing to say is that we want potential energy sources to have positive gradients and curvatures at close approach. So do you think this kind of statement could be worked through a similar analysis?
Yes, I think so. I mean, I suppose, because, you know, here I mentioned that it's nice to have these as expectations, but even if you don't have them as expectations, you can still, it just becomes messy. But basically the maximum entropy, it just says you apply any constraints you want, and well, I mean, as long as they. So the question is, how would you sort of write it down mathematically? And you know, we can think about it, for instance.
Questions? Okay, so thank you again. Where are you? Guys, from Cambridge. Okay, so Cambridge, and the title of his talk is Hyperactive Learning. Great title. Okay.
Thank you very much. Yes, so today I'll be talking to you about hyperactive learning, which with David, another PhD student in our group, with Gabor at the University of Cambridge, and Matthias at the University of Birmingham, which is a former postdoc of Christoph Schran. And what we're going to try and do and talk today about is building minimal training databases for these data-driven interatomic potentials, and trying to figure out, like, how can we sort of create databases in building these potentials, which are actually sort of efficient and reduce the time you actually spend creating these databases. Because it turns out that when you create these potentials, quite a lot of time is actually spent in figuring out what training points you need, and where do you actually mine the data in order to achieve a good model, essentially. So first I'll talk a bit about the atomic cluster expansion, but Christoph did that bit on Monday, and so I won't spend too much time on that. And then we'll discuss briefly about this idea of minimal databases, and that sort of ties into what I was saying earlier as to how much data do you need to describe properties well, like bulk, amorphous, or liquid properties, and we'll do that for silicon. And then we'll introduce hyperactive learning, which essentially biases active learning towards uncertainty and trying to generate particular configurations which are sort of far away from your training database, but still sensible in a way that actually improve your model and make a good interatomic potential, essentially. And then I'll finish off with some results on a polymer for polyethylene glycol and also some alloys, and we'll see how far we get. And I'll especially want to show the first one, which is simple binary aluminium silicon. All right, so the atomic cluster expansion is a systematically improvable set of polynomial splitting atomic energies. I think we've seen this a few times before already. This conference where we first decompose the total energy as a sum of atomic energies, and we try and fit that as sort of a function of its neighboring environment, which is given by these relative bond vectors around some central atom. And you can express the atomic cluster expansion in several different ways. And what I'll be leveraging is sort of the linear way of doing that. And by linear, I mean linear in the coefficients, right? So evaluation of the A spaces, basically the energies would just be expressed as a linear combination of a coefficient vector times by the basis evaluated on your configuration. And since you express as a linear model, the only thing you have to do is essentially do linear regression, which is a very straightforward technique. And for this talk, we actually look at some Bayesian linear regression, which takes a Bayesian view over the simple linear regression problem. Right, so that sort of sets up a statistical learning problem where you effectively assume there to be some noise on your observations, and your observations are collected in Y, which can be your energies, forces, or variables. And then the psi is your design matrix, which you're trying to fit. And for a Bayesian approach, we know that you achieve the posterior by first choosing a prior and a likelihood. And I think we've also seen this a few times before, in that you can use a simple sort of spherical Gaussian as your prior, given by your variance alpha -1, and that turns out to be equivalent to Bayesian-rich regression, which we've seen before. Another way, which actually relaxes this single alpha for the coefficient hyperparameter, is automatic relevance determination. So what that does is it essentially assigns a different alpha for every different coefficient, which in turn gives it its own hyperparameter and actually determines the relevance of a particular coefficient and the relevance of a basis function actually being relevant of your fit. Next, we have to set up a likelihood, which we're just going to use as a simple Gaussian, and which was given by this beta term here at the bottom, which will set effectively your noise level. And what you then do is you use hyperparameter optimization to essentially determine these alphas and betas. And the nice thing about keeping everything in Gaussians is that also your posterior is a Gaussian and everything remains in a closed analytic form. So your posterior over your coefficient space then looks like this, which is a probability distribution over your coefficients, which is defined by a mean, mu, and some covariance matrix you can easily obtain using your determined alphas and betas in the design matrix, which you can sample a whole bunch of different committee members from. And I think the nice thing is what we've talked about before, and I think Chiriotti was saying on Monday, is that this kind of allows you to have some cheap committee predictions, right? Because when you perhaps want to run some dynamics or you want to do some NG evaluations, what you can do is you can sample lots of C vectors before you run the dynamics, and you have to evaluate the gradients once, and then you can just dot in a few different C vectors or your mean parameterization to get different predictions. And actually what we can do using these cheap committee predictions, particularly for the forces, we can actually set up some relative force uncertainty, which I'm going to call this U. And what that essentially does is it looks at sort of the force difference between the mean parameterization, which is in orange here, and your C vectors, which are these green vectors here, which are all sort of committee predictions around the mean, because the mean is the center of this distribution. And then by dividing that by the mean force itself, you can get some relative force uncertainty, right? Because this kind of normalize the fraction. Obviously, you need to be very careful in that if you divide by a small force, that fraction will explode. So that's why we have some delta F here, which just regularizes the fraction because you don't want it to blow up. And we generally set it to around, say, 0.2 eV per angstrom. Sort of forget about it. The nice thing about this quantity is that it's first of all local, so it probes local uncertainties on your model, right? It's not some global thing. It's also relative, and I think relative is a good error metric to look at because a 10% error generally is sort of good for a whole range of different observations, right? So if you want to have run liquid, you have 10% error, that is generally acceptable. But if you want to fit a phonon spectrum where you really care about very tiny forces, then 10% is also often sort of where you want to be, perhaps a little bit lower, but thinking about relative force errors, I think works quite well. And obviously, because it's relative, you need to regularize, because otherwise it blows up. All right, so now we get into this idea of minimal databases, and we're going to try and effectively reduce a large silicon diamond database that was assembled by my supervisor and James, I think, as well. That worked on a large silicon database, and one particular configuration type is silicon diamond, and it contains 489 configurations in 16,807 environments. And you can ask yourself, like, how much data do you really need? And so what I did is I started with a single configuration and just looked at sort of the largest relative uncertainty inside a configuration of the test configuration. And if it's the largest uncertainty, I added it to my training database. I sort of iterated that idea. So every configuration with the largest relative site uncertainty, got added to the training database, and iterating that gives you this red line. To benchmark this, of course, I benchmarked it against random selection. So I started with the same configuration and then just randomly selected from the test configuration, so the remaining configurations. And you can actually see that you accelerate the learning curve pretty dramatically. And actually, you sort of generalize already after using about 5% of the original database. And that's sort of quite interesting, right? And actually, we should investigate a little bit further. And you can actually look at the error correlations along this sort of this trajectory. So what you can see after having 4 configurations in your database, and you look at sort of this maximum relative force uncertainty over your remaining configurations and the maximum relative force error in the configuration, you can actually see that you are managing to actually predict and find these configurations where there is remaining large error And actually, by adding those to the training database, your max relative force error also goes down over the entire test set. And you can see that everything sort of starts to converge quite well after only 16 iterations. Obviously, there's this point here at the top, which still remains to have a very high force errors, which is a bit unfortunate. But as you can see, we are generalizing quite well. But obviously, we're more interested in actual properties, right? So what if we look at these properties? You can actually see that if you look at these energies versus volume curve, the configuration that's selected along this filtering process essentially are these configurations on the outer spectra of the spectrum of the volume curve. So what it's doing is finding these configurations, if you look at it in this dimension, on the outsides of the volume spectrum, and just regularizes quite well and manage to capture the energy volume curve pretty good. Next, the elastic constants, as you can see here, using only 3% of the original database, you have pretty large errors on the elastic constants, but then adding a few more points actually achieves very good errors on the elastic constants. And I think what is perhaps most interesting are these phonons, right? So in order to get phonons right, you need to have low relative errors. And by sort of formulating it as a relative error problem and optimizing that problem, you actually see we also squeeze the error on the phonon spectrum as well. And if you don't look at relative error and you only look at large force errors, what happens is that you sort of automatically look at large forces, and you would never have a good phonon spectrum, right? So you actually need to look at large relative force errors. Also, thermal properties like the heat capacity and the thermal expansion, you can see that also there we actually converge quite well to the properties. So, and I think this is quite nice, right? So we've effectively reduced the training database by a factor of 20 for the diamond database, and for the vacancy we could do a similar sort of reduction. For the amorphous and liquid, a bit less, and I think that's not surprising because you will need a bit more data to actually describe these more diverse training data, these more diverse configuration types than just simple crystal structures. I don't think that will surprise anyone. But this sort of is a build up to sort of, can we leverage what we've learned here and actually building these minimal databases from scratch? Because this was just a filtering exercise. Can we actually use what we've learned here to build training databases from nothing? And that's actually where hyperactive learning comes in. And the idea is actually quite simple. What we do is we fit some model, and using this Bayesian framework, we can actually determine the variance on some test configuration, and actually more specifically for this exercise, the standard deviation, in order to make the units work out here, right? So by effectively subtracting the standard deviation on a test configuration from the potential energy surface, what you do is you actually assign lower energies to configurations with high uncertainty. And then if you run dynamics where you explore low energy configurations, what happens is that you actually end up in these configurations that actually have high uncertainty. And that's actually good because that sort of biases you towards trouble as you run dynamics and leads you to configurations which are far away from your training database, which actually is what you need in order to build a good training database and sort of have a good model. So if you take the derivative of the first term, the energy term, obviously you just get the forces, but for the second term, we get something a bit more interesting where you see the gradient of the standard deviation is the same as the gradient of the variance divided by the standard deviation. And what happens is that the inherent noise term drops out, and effectively throughout using the chain rule, you get this large vector matrix vector multiplication at the top here, which is kind of expensive to evaluate. And actually what we can do here is, again, use that committee approximation to essentially approximate that same term here at the top, which is much cheaper to evaluate, because at the bottom, the only thing you have to do is evaluate the gradients ones and the basis ones, dot in a few different C vectors, and you can actually sort of approximate this biasing term, which can actually interpret as a force very cheaply while you're running dynamics, which you could then actually add to your molecular dynamics and bias towards uncertainty. So if you look at the equations of motion of hyperactive learning, what it really is that you have the F mu, which are your molecular dynamics forces, plus perhaps some F gamma, which is your Langevin thermostat, plus some extra term which biases you towards uncertainty. And this is scaled by your parameter tau, which is a biasing parameter, which is of course very hard to control, right? Because you kind of want to still follow the original potential energy surface, but you still want to bias it gently towards uncertainty, and you don't really want to sort of quickly generate very unphysical configurations. And the way we're sort of managing to control it is using some adaptive biasing terms. So what we do there is we essentially look at the magnitude of this uncertainty force and the MD force, and we sort of tune it to be, say, 5% or 20% of the MD force, such that you gently nudge it as you run the dynamics towards uncertainty, trying to bias it towards trouble, essentially. And then once you get to trouble, the question is, how do you actually, just before you start to really extrapolate too far from your training data, when do you actually stop and say, all right, I need to trigger a DFT calculation and add it to the training database? And the way we do that currently is essentially by applying a softmax function first to these relative uncertainties. So you have essentially a vector of relative uncertainties of your entire configuration, and then by applying a softmax, what that does is it scales everything from 0 to 1, but it also has some extreme sensitivity to any sort of sites having an emerging uncertainty on it. So what happens is that you run dynamics quite well, and then if on one of the sites the committee members really start to disagree relatively to everywhere else, the nonlinearity of the softmax will effectively have some increased sensitivity and really give you a strong signal. And you can set some U tolerance measure, which is predefined, and say, once it hits that, you say, all right, stop, run DFT, add to the training database, and sort of build a training database like that from scratch. So now we get to some results. Here is some BEC2, which is a polyethylene glycol. It's a sort of a 2 monomer long polyethylene glycol. It's a pretty small molecule, and what you can do is you can actually think, all right, let's use a very simple ACE model, which is not very perhaps not super accurate, but it is sort of something nice we can work with correlation order 3. So it has 4-body interaction for lobule degree 10. And what we can do is you can say, all right, how many time steps do you have to run your active learning or hyperactive learning in order to achieve 1 million of these steps without failure, right? And as you can see that without any biasing, you have to do around 33 iterations of finding new configurations and doing about 10 to the 6 time steps in order to achieve MD stability. Whereas if you use some biasing, that reduces to 10 to the 4. So what that means is that you actually end up having to run many fewer MD steps in finding these uncertain configurations and actually create a model that is much more stable, much faster than without any biasing. So that is kind of nice, because you kind of want your models to fail quickly when you run active learning.
How does the number of DFT calculations compare?
So that's the number of iterations. Sorry, I should have said that. So that's actually less impressive, right? I mean, that's sort of a bit fewer, but not that many. It's actually, I think, really the number of time steps that is reduced because you get there quicker. But
you're just having one snapshot.
That's right. Yeah. So you once the tolerance gets reached, you say, all right, run DFT, add to training database, and start over. Perhaps a more realistic scenario is where you maybe have some large destined training splits, and for 800K and 500K, and they all lie on the diagonal, and you're quite happy, you think you've got a good model, but then actually when you fit that database, you start running a HAL, what you're seeing is that you can actually find all these configurations far away from the diagonal, which actually have very large errors on them. And these are the configurations actually that you find by biasing towards uncertainty, then sort of stopping, grabbing the configuration, and when you evaluate the DFT, you actually see that the model actually had very large error on it. And this is also the configurations that would often lead to MD failure, because.
And these are still very low energy configurations, right? So it's not that these are.
That's absolutely right. So that's a good point. And actually, what you can see is that often these configurations kind of look like this. It's kind of interesting. They seem to exhibit some hydrogen bonding, which I think Boris Kosinski would call sort of rare events, but they are very important. They are low energy configurations if you look at DFT, and you will actually explore them if you run MD long enough. And if you don't get them right, the MD will explode, right? So these are, rare events, holes. It depends on how you want to call them, but you actually need to incorporate them into your model without, because otherwise your MD will fail essentially. Essentially, we can use a similar process to keep adding data, and you can go up to BEC 32. And because the atom gets larger, you're starting to see that you really need something that is quite local, right? Because if you look at this long chain here on the left, you see this one hydrogen in a bit of a funny position, which would lead to MD failure, but our uncertainty metric just pick it up. We evaluate the DFT, add it to the training database, and at some point, your model is stable, and you can actually start running long polymers, right? So here we have some periodic boundary conditions, and we can run it at 700 Kelvin, and this is 1,400 atoms, and it is a long polymer above the melting temperature, which, yeah, it's going, and you can actually see that this is a particularly hard polymer to do because it's very floppy, and it's got lots of different directions it can do, and lots of different ways it can fail, but we are managing to find those particular configurations, adding them to the training database and creating the model. All right, so now we get to the alloys, which is actually what I've been working on throughout my PhD. So here I start with 32 atom aluminium silicate 10 alloys, which I first generate, say, 10 random alloys over a range of different volumes around the minimum. And what I do is I fit it, use 32 committee members to start running hydrodynamics. And for these alloys, what turns out that works quite well is you can actually, especially during the random alloy stages, that you do swap particular alloys and adjust the volume according to this new augmented potential energy service, right? So what you do is you do swaps and volume steps and try and really explore different environments. And so you can see different iterations here. So for the first iteration, you do a few volume steps and swaps, which kind of makes the pressure go a bit up and down. And then you can see the temperature goes up. We run it at 800 Kelvin, and after only 200 steps, we actually find a configuration which is troublesome, run DFT, add it to the database. And then at some point, you actually see that nothing really comes up anymore, and you've actually learned the random alloy. And we can do a similar thing for the liquid. Obviously, you would not be adding random alloy swaps or volume steps, where you could just use thermostat and parastat and essentially increase the temperature and have some pressure set and generate lots of data for the particular pressure and temperatures you're interested in. One thing that I think is quite interesting here is that you can look at some test error convergence. So here I have some test set generated, and I basically look at the configurations generated and the amount of steps to generate that database, and look at some test set error convergence. And so if you do Bayesian ridge regression, simple L2 regularization, you can see that you have some learning rate, but actually by biasing, you accelerate that learning rate quite significantly in red. However, what also really helps is using these sparse models and these sparse ARD priors to really filter out the right basis functions and actually really capture the potential energy service even better, which accelerates the learning curve even further. And then adding some biasing is sort of the fastest way to really learn, really reduce the test set error on some test set for some aluminium silicon 10 test set, which is quite interesting, right? So ARD plus biasing actually really accelerates the learning rate and actually really allows you to drive these training databases to pretty small sizes. And as for example, here you can look at this database I ended up with using 42 configurations for random alloys. They're all 32 atom in size, and 46 configurations for the liquid. And if you then assemble the design matrix, it's quite small. It's about 9,000 observations, which are the energies, forces, and variables, and a small A space of around 723 basis functions. And what you can then do is you can use these ARD fits to try and do different fits with different ARD relevance thresholds. And what this does is it kind of sets the minimum relevance required for adding a basis function to the fit, right? So as you can see, when you increase the relevance, more basis functions get included. Fitting time also goes up, training error goes down, and also the test error goes down, right? So you increase the number of basis functions you use for your fit. You have effectively a more high resolution fit of your linear problem, and therefore the training error comes down, which of course also increase fitting time, which is here shown in seconds. And that's, I think, the nice thing. By reducing these databases, you can actually start fitting these models on your iPhone. So these are, this is on your A14 chip on your iPhone. You can fit these models in about 4 seconds for these 116 basis function fits. And they actually capture the random and the liquid description quite well, as you'll see in a minute. First, we'll have a quick look at the basis functions. right? So as I was saying, increasing the tolerance adds more basis functions, and you can sort of see that here. So these are the basis functions, and this is the absolute magnitude of the coefficients on them, and using sort of the low alpha prime threshold, you can see that there's only very few configurations, about 38, and then adding more and more basis functions, you can see more points appearing, and then for the black curve, for the black 300,000 AOD threshold, you actually see many of these black dots, especially in this lower region at 10 to the -3, and you can you ask yourself, well, actually, are those really relevant basis functions? And aren't we sort of starting to overfit? And actually, if you look at this test set error, that seems to be what's going on, right? So if you look at the force for the test set error goes down, 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 and then for the 300K, it actually goes up again. So it seems that you're actually starting to overfit a little bit and actually use too many basis functions to really capture the potential energy surface, which I think the plot kind of illustrates as well. And then we can start doing interesting things like, for instance, nested sampling. So people, I think, will know what nested sampling is here, but I don't really have time to go into it. But what that does is it really approximates the partition function by determining the cumulative density of states. It's a bit of a mouthful, but anyway, what you can do is it's a way of determining the melting temperature. And what you can see is that sort of using these very simple descriptions with very few basis functions, the training error remains high, tested error remains high, but also the melting temperature is still off, right? But then improving your model, adding more basis functions, training error goes down, and also actually your melting temperature estimate turns out to improve as well. And you can actually see that we achieve effectively or pretty much bang on melting temperature with regards to experimental predictions perfectly using these models. And these fits only take essentially 16 seconds to fit, which is quite nice, I think. And that's also why I think this framework is quite nice, is because the fits are pretty rapid. The active learning process of the hyperactive learning is pretty rapid in the sense that you only have to evaluate the few dot products, you run the dynamics, you find configuration with high uncertainty, and then the really thing that remains very costly is the evaluation of the DFT, but that's also with CPU, with larger nodes becoming available, that's also becoming more and more simple. So actually you can build these databases in days essentially, which is quite nice. Then next we have a few more results. I'm not sure how much time I have got left.
Just 2 minutes.
Just 2 minutes, all right. Well, basically we can do all kinds of things now. So you can add some magnesium, and you can have a look at what sort of configurations we form here, and we're actually seeing some clusters form in magnesium now as well, and we see some perhaps slightly unconverged nested sampling results because it's really expensive, but these clusters are actually what give this particular alloy its interesting properties. And these are GP zones, and it's actually a metallurgy, actually, what we're seeing here. And that's sort of quite nice to see. Then there's molybdenum, niobium, tantalum, tungsten. It's also an interesting alloy, which has actually disorder transformations at low temperature, and people like its properties at 300 Kelvin because the niobium and the tungsten actually are disordered, whereas the molybdenum and tantalum remains ordered. And we can actually have a look at that using these short range order parameters. And all these databases are built effectively using this process I was talking before. And it's perhaps not really about errors, but what I'm trying to show you is that using this process, we can assemble these databases pretty rapidly, and we can start doing effectively more interesting science on high entropy alloys as well. Because here's the Cantor alloy, which we achieve with pretty good accuracy. But I think it's time for questions. All right. So yeah, are there any questions? These are the conclusions, I guess, where we just a quick recap. We sample committee members from the posterior for these linear ACE models, which is actually quite straightforward to do in this Bayesian linear regression framework. We get cheap committee evaluations, have this relative force error that we managed to reduce the training database with, and how biases and lead towards uncertainty. And using the softmax, we have achieved increased sensitivity on emerging uncertainty, and this is how we can build these minimal databases automatically and efficiently from scratch for polymers and alloys. Right, any questions?
A couple of online questions.
Christoph.
Yeah, I hope you can hear me fine.
Yes.
Perfect. Okay. Yeah, very nice talk. I really like this idea of essentially like biasing towards like higher disagreement, and was just wondering, like in principle, you essentially want to prevent too high disagreement. So have you maybe also considered like biasing for intermediate disagreement somehow by adding another term that would essentially prevent a situation where you are just too like extreme? Or did you already mention that? I wasn't sure. Maybe you could go over the details there again.
Yeah, so I think what you'll see is that this effectively comes down to this biasing term, right? So if you have very strong biasing, you very quickly get to very unphysical results. But in principle, if your molecular dynamics is sort of okay, then you stay on this manifold, which should be okay in terms of generating valuable configurations. So I think this kind of ties into this whole tau parameter, this strength of the biasing, which we're currently doing in some adaptive fashion, where we tune it according to the sort of the uncertainty as seen before. And actually what it also does is it increases when you're in very certain regions, and it decreases when you're very uncertain regions, because you feel like you have less control over what's going on. That seems to work quite well, but yeah, I'm open for suggestions if you have better ideas of how to do that.
All right, thank you. Yeah.
I have a follow-up question.
Okay, fine.
Christoph, why would you want to bias away from large errors that are nearby low energy configurations?
No, it's just that like if you are biasing too much, right, you essentially explode, and then it's unphysical, right? So I was wondering, like, you probably want the sweet spot, like of like intermediate disagreement where.
But it's the question of catching as it explodes. So I think it's the two different issues. Which way do you want to go, and then when do you catch it? If you don't catch it soon enough, you're right that you just have this isolated crazy point. But
yeah, right. So your algorithm is coupled like to the DFT directly, right? So you essentially stop, refit, and then right, yeah, okay, yeah. Then you probably don't really need that. Yeah. Okay, thanks.
What time? One short question.
Yeah, one short question, but almost please.
Can I ask a question?
Sure.
Follow up. Hi, this is Boris. Nice talk. Very interesting approach. I was wondering, is it a fair comparison when you turn off biasing and just stay on the true potential energy surface where you just follow MD versus now bias towards uncertainty? Could it be more fair, for instance, to just instead of biasing towards uncertainty, compare with a random kind of term added to your exploration to show that, you know, biasing towards uncertainty versus just randomly perturbing away from the true surface is also better? Because I mean, you will be exploring more for sure if you go outside of your true potential energy. Have you had any sort of results in this kind of direction?
Not really. I haven't really thought about it in that way yet, but I see what you mean. Yeah, I should certainly have a look at that. I do think that a good sort of test, though, is achieving MD stability, because it can be quite hard in building these models. So maybe I should add that to that table. Perhaps that's a good point to that. So that is a problem, right? Because by introducing essentially this extra gradient, you are sort of modifying the potential energy surface, and the question is, are you now sampling something a bit weird? I think the only way to really figure that out is to look at properties, right? So look at maybe some glass transition temperatures or other properties, which you should still get right. And if you can achieve that using biasing, then I think it's a good idea to do. But yeah, this adding some random direction is interesting. I'll have a look at it.
Okay, thank you.
Okay, so welcome to this last session. There will be 2 online talks of 30 minutes each. So the next and the first talk of the session will be given by Khachik Sargsyan, and it is on model error estimation and UQ of machine learning interaction potentials. Please go ahead.
Thank you very much, and thanks for the invitation to speak at this workshop. Yeah, the talk will be more of a methodological work that we've been doing on estimating model errors in MLIPs. My colleagues, co-workers on this are Logan Williams and Habib Najam. And I do want to get acknowledgements out of the way. It's Department of Energy funded work, and our colleagues from both Sandia and an intern, Katie Johnston, has helped quite a bit. She's a grad student at the University of Washington. So this overall outline I have seen a couple of days ago from Habib Najam's talk. This is very generic picture of the project and also I think workflow that many of you can relate to. But I'm highlighting the UQ aspects of it, where we are building Bayesian building of MLIPs enabled by model selection, active learning, and subsequent propagation via forward UQ methods, and also final sort of experimental validation that can also impact and help inform the MLIP construction as well. But this is a really big picture, and most of the pieces are for another day. I'm really focusing on top left corner of this, where Bayesian fit of MLIPs. Let's assume DFT is correct. I'm not dealing with DFT errors. I want to talk about uncertainty augmentation with model error in MLIP construction, and that's needed, of course, for propagation through MD simulations potential, or active learning, or model selection strategies. And the work will be, as I said, more or less methodological with only a few results shown applications. The work is on Bayesian approach with a slight focus on linear regression models, because we can take some shortcuts when linear regression. SNAP is a sector neighbor analysis potential that many of you are familiar with, and we are working with Aidan Thompson, who is the lead on the SNAP, of course. And I'll discuss about the importance of noise model and embedded model error construction I'll try to introduce, and relate it to sort of more or less well-known variational inference strategies. So I had many introductory slides that really don't need to be here anymore. I removed most of them, only left this one. This audience, everybody is familiar. So we have the clear signature of a supervised machine learning problem. Basically, we have Cartesian inputs, perhaps some feature extractor, fingerprints. There are many possibilities, of course. And typically a functional form that's parameterized, maybe with the exception of Gaussian Gaussian approximation potentials. Usually we have parameterized MLIP form, and then come the FT ab initio data and some kind of error metric to fit these two together, right? So this is the setup, is a supervised machine learning or regression setup in principle, and there's all of you are familiar with this. And what do we want with this from these MLIPs? This is a probably incomplete laundry list, but the key is that we really want to equip with uncertainties, equip them MLIP prediction with uncertainties, specifically because it's going to help us for active learning, for model selection, and for UQ or uncertainty propagation through further MD simulations. So so let's talk about this in more detail, enabling parametric fits with uncertainties, and what are our options. Typically, there's plenty of methods, as you all know, and there is a spectrum of sort of descriptor or fingerprint approaches, right? Where you can have many complex ones like bispectrum or ACE, to a very simple sort of raw input that's Cartesian, right? And similarly, there is a spectrum of models in IAP construction, right? From linear regression, relatively simple models, to heavy and heavily over-parameterized, something like neural network, right? And often this come together. You put a lot of effort into descriptor and fingerprint construction, and then you can live with a simpler model, or vice versa. You don't want to put a lot of effort into descriptor construction, but let a heavy model to learn it, essentially, right? And now I'm adding this third row, essentially. In this picture, the UQ methods. Also, clearly, there is a spectrum of approaches, and usually it's married to the model complexity, right? So if it's a linear regression, certainly the Bayesian method is way to go, but when it's linear regression, often we can get away with analytical results with correct proper assumptions, or if we don't have a closed form solutions for Bayesian posteriors per se, we can do MCMC sampling, right? And then as models get more complex, maybe something has to give, right? So or there are approximate methods, including variational inference methods that also often are just called Bayesian methods, all the way to the sort of most complex models where Bayesian and even variational methods might not be an answer, and the more heuristic empirical approaches like ensemble, deep ensembles are sort of way to go, and probably the only way to go. All right, so let me focus at least initially on the left part of the spectrum, focus on SNAP. This is many of you are familiar with the spectral neighbor analysis potential, where there are input features that are bispectrum, and the problem model itself is a linear model, really linear regression. In many cases, as I said, both MCMC is feasible, but also analytical posterior PDF computation is feasible. And by posterior PDF here, I mean the posterior PDF on the coefficients. These are the parameters of the model CKs, right? Again, we have seen this type of formulation many times this week. In general, the parameter inference can be lifted to Bayesian realm, of course, given a model and data, whether it's a linear model or nonlinear model, really. Bayesian least square fit is the usual least square fit lifted into posterior prior language, but it allows you to be more explicit about your noise assumption and data model, right? So for example, the typical least square fit, unweighted, let's say, it corresponds to a data model here in the third bullet, that your data is the model plus some IID Gaussian. Again, Bayesian method kind of allows you to be more explicit about these assumptions, and actually it reveals issues with the assumptions as well, of course. And for linear models, particularly when we have this simple assumption IID Gaussian noise with constant sigma, there is an analytical answer basically for the posterior. So you start from let's say an informative flat prior for simplicity, and you get a posterior that's multivariate normal with mean and covariance that are analytically available. Of course, there is an issue with that. In general, for example, this is a simple tantalum data set where on the left top is a model fit that seems to be doing the job, but when you zoom in, some regions of the model are fit well with uncertainty, and in many regions, uncertainties are basically negligible. This is one sort of reincarnation of why constant sigma assumption is bad, of course, because you see a multi-scale data points, and on high values you heavily underestimate the uncertainty, right? So just a point to make, and again, many of you probably are familiar with this, the assumptions baked in the Bayesian likelihood are crucial, and IID Gaussian noise with constant sigma is most of the time not a well-founded assumption. So what is the elephant in the room? Of course, elephant in the room is the model error, right? So the data model that we start with that says DFT is the IIP plus sigma I epsilon I, basically. That data model assumes the model is the true model behind the data, which it never is, right? So with this assumption, you always get biased estimates of parameters of your model, or coefficient of SNAP expansion, or weights of neural network, if you wish. And this is extremely important if those parameters are sort of have some physical meaning or need to be piped down the line with through some MD simulations, right? Particularly, it's evident when there is no real experimental error and DFT is the data and MLIP is the model. There is no reason to believe that the discrepancy has to be IID, right? Independent identical distributed. And more data leads to overconfident prediction. This is another sort of issue that comes up when you assume model is the true model behind the data when it is not, right? And this is a very simple toy example that kind of demonstrates it. If you have a synthetic data set, and let's do cubic polynomial fit, really, I apologize for a very, very simple example, but I hope this brings the point home. You have, if you start from 7 data points and fit a polynomial, things are reasonable. Wherever you have data points, the fit is good. When you don't, it's not. There is no much you cannot expect really. But as you increase the number of data points, you get a fit that becomes, well, because your model is deficient, the true data is not a cubic polynomial, right? Your model is deficient. This is the best you can do with a cubic polynomial. But the bad thing is that the pushed forward uncertainty does not capture the true discrepancy, right? The push forward uncertainty that's built in this coefficient, you become, it becomes narrower and narrower. You become more and more certain about the wrong values of your physical parameters, right? And how do people go about this? Usually capture model error in the data model. As I said, that's sort of necessary. And in statistical literature, it's very common, and seminal work by Kennedy O'Hagan suggests adding a Gaussian process to your model outputs, and you can sort of infer and feed the Gaussian process together with your model parameter C as a sort of bias correction on the output. What we suggest actually is a slightly different approach that is better working for physical models, where you embed statistical corrections inside the model, whether you inflate some parameters with uncertainty or you actually go under the hood and change the model. But the point is to make these corrections inside the model rather than outside, because that, first of all, it will respect the physics. It will be allowing meaningful usage of the calibrated model across many observables or quantities of interest, output quantities of interest, while the external correction is only specific to the data that you use with, right? You don't know it's part of the model or it's not the part of the model. But embedding allows you to be meaningful about these things. And leftover noise is always there, even if you have infinite amount of data. And you'll see in a simple example next on the next slide. So usually there is, of course, a challenge. In order to construct the likelihood, you need some sort of uncertainty propagation from inside the model to outside. And that can be done using polynomial chaos machinery, etc. But I'm not going to talk about that, particularly for linear regression. That propagation is simple enough, so we can take some shortcuts, really. So once again, the conventional method says that the data model is your regression expansion plus IID Gaussian noise. If we embed in all or selected coefficients of your model, you get this type of expansion where CK is standard Gaussian random variable, standard normal random variable. And of course, there are many choices where to embed, what type of embedding needs to happen, etc. But the key is that we are lifting a deterministic coefficient or parameter of the model C into a probabilistic realm. We are assuming some sort of distribution on it. And then that in linear regression easily allows you to rewrite exact data model where you can split the model from the model error, right? So in this case, there is no formal distinction between internal and external corrections, but the error now is different from the IID Gaussian. It's actually model-informed error. But there is no free lunch. This model-informed error is low rank, and it will require you to do some sort of approximations of the likelihood on the outside, as you will see in further slides. So typically, again, conventional one is a MCMC inference of parameter C on the top, and embedded one now will be formulated so that we are inferring parameters of the model as well as parameters of this model error statistical correction together in one Bayesian framework. There are issues, likelihood and prior selection, that are probably stories for another day, particularly the prior selection. But what's useful here to recognize that even if MCMC approach is difficult, and it is difficult because posterior surface is quite hard to sample from, you can still just do optimization and come up with best answers of C and D, and that will still leave you with leftover uncertainty in your model that doesn't shrink with more data, right? So there are ways to go about it. If the posterior distribution is really difficult, but we are only interested in model error, we can just live with simple optimization and not do MCMC. And so a couple of options of these approximations. Again, likelihood is challenging because there is sort of no free lunch. If your model is, if your data is not a cubic polynomial, you're trying to fit it with cubic polynomial, no matter how much you augment uncertainty in coefficients, your form hasn't changed. Your form of your model hasn't changed. So the likelihood is degenerate. It's really non-zero only on a small, lower dimensional manifold. So some approximations have to happen. But here approximations are happening on the outside rather than on the beginning. You know, when you say I have IID noise, here the approximation is on the likelihood end, basically. So one approximation, option one, is IID, basically, when we say let's split the prediction distribution into pieces, basically the product of marginals. Another one is a sort of goal-oriented type approach, similar to approximate Bayesian computation approach, where you're just matching certain metrics on the output, right? So I want my mean prediction to be good with the data, but I also want the predictive standard deviation to be within some factor of the true residual that I'm committing, right? So this is sort of a goal-oriented approximate likelihood that allows you to sort of build in the type of assumptions that you want on the output into your formulation. And as I said, that doesn't have to be MCMC, because this can get very ugly in terms of posterior distribution, but simple optimization will give you parameters of model error as well as your model parameters together. And a demonstration on that simple example. On the left is the classical case where we heavily underestimate the uncertainty. On the two right plots, where there are the two options, and in ABC likelihood, you see on average, we're kind of capturing the spread of the data, the residual. On the middle one has issues, and I think this needs to be regularized with better prior selection. That's work in progress, but it kind of snaps into a few regions where you have zero uncertainty, that and then sort of has extra bit of uncertainty that captures the model discrepancy, just the way it's built in the likelihood, right? On the two example, well, in this case, one example, zirconium carbide, tungsten zirconium carbide data set. On the top, we have the sort of classical form where the data is compared to the fit. Blue is training and green is testing data, particularly focus on the top right plot, where the one standard deviation prediction interval really does not capture a lot of data points, and even 3 sigma, you can sort of mentally see that we have many outliers. That means residual is larger than uncertainty. We really don't want that to happen, right? But when you augment internally with model error, you get much fairer picture, and you can get a 3 sigma region that captures pretty much all the residuals, and that's better to be conservative, definitely, and have uncertainties where you are not very close to the true data. It's another way of sort of showing how the uncertainty is validated on two different examples, top row and bottom row. The conventional method on the left shows that there is a huge discrepancy between predictive quantiles and the actual data fraction that respects that quantile. This is the typical uncertainty calibration sort of picture, and the two right columns are the options where actually embedded method gets this quantile picture much closer to the diagonal. That means we have a much better calibrated uncertainty in this case. So as a sort of a wrap up, before I kind of just change the gears, this is the embedded model error approach that we have originally developed for sort of more physical models and non-linear models, but some shortcuts are allowed when you have linear regression, but this is more or less a work in progress. But sort of think of it as a tool to explore your model in terms of model error. We will never get to actual exact model error estimation correct, right? Because otherwise you would have just improved the model. But this is sort of a tool to analyze your model in certain places to understand where are the highest model errors committed, et cetera, given goal-oriented likelihoods. So many choices to make and many challenges, including embedded type, additive, multiplicative, right? What type of likelihood to use, what type of priors to use in physical parameters like coefficient of expansion, or those are more or less kind of physical. We can understand and come up with reasonable priors, but what type of priors to use in embedding parameters, that's yet another question that needs to be really understood. and weighting between energies, forces, and stresses. Mostly I showed energy results, but it really doesn't matter. However, in this particular application, there is really one needs to pay extra attention how to weight between different types of data points, right? So I'm switching gears a little bit in this spectrum, bringing it to the middle. Variational inference is a common compromise between Bayesian and empirical approaches when your model is somewhat difficult. What is it in a nutshell is, instead of the true full Bayesian posterior, we come up with a class of parameterized posteriors and find the best one in that class that's closest to your full Bayesian posterior by some metric, typically KL, Kullback-Leibler divergence between two BDFs. And what's this class of parameterized variational posteriors? Well, there are many ways, but the typical sort of a standard one is this mean field variational inference, where you ansatz your coefficients to be multivariate normal or IID normal and find the best parameters that control this normal. Again, minimizing this Kullback-Leibler divergence between your variational posterior and the true posterior. And there are tricks where this KL can be written in certain forms that makes this optimization feasible. But the point is, the bottom line is that this replaces the sampling problem like MCMC with an optimization problem that's easier to solve typically. I do want to note the connection between this sort of common variational inference and the embedded model error approach. Both kind of lift your deterministic coefficients into a probabilistic realm, right? Both are saying my coefficient is, in this case, multivariate normal, and let's optimize for parameters of that multivariate normal. In neural network context, by the way, variational is often just referred to as the Bayesian neural network, but MCMC is typically infeasible, so variational is the go-to BNN sort of replica. But the key difference is that in variational methods, one minimizes Kullback-Leibler distance via stochastic gradient descent, and in embedded model error approach, we, as I said, we minimize two different types, as I showed, of likelihoods or posteriors, if you wish. But mechanically, very similar. I do, however, want to have a couple of slides that sort of shows some issues with variational inference with Kullback-Leibler minimization in overparameterized linear regression regime, kind of mimicking what neural network does. It's an overparameterized model, right? Particularly when we are outside training support. So it's a sort of, again, yet another toy example, but in a linear regression, variational posterior, mean field posterior can be, the KL minimization can be done analytically without having to be at the mercy of stochastic gradient descent algorithm. Just for cleanness of the test for linear regression, we did this analytically to understand what's the best variational can do, mean field variational can do, right? So when you have a data set and you're fitting a second order polynomial in the region where you have training data, you can see the inset. Both are doing reasonable, and in fact, they are equivalent in some ways. Right, and outside, you already here see that variational inference heavily underestimates, outside your training support heavily underestimates the uncertainties, while the full Bayesian posterior does not. And you increase the order, you can, the same picture, you know, in the training support you're doing well, outside not so much, and that's very important for us, particularly if we want to feed into this, feed in this uncertainty into active learning approaches. We really want to be sort of respecting the extrapolation regimes, right? When we don't have training data, we want our uncertainty to kind of show us that. As you increase the order, it's exactly the same thing. In the training support, everything is good. Outside, things go crazy, but they should go crazy because you don't have data there. The same thing with interpolative scenarios where your training data has holes in it, right? The same idea holds. Basically, as you increase the order, you become more and more over-parameterized, again, mimicking kind of like a neural network type approach, right? Variational posterior underestimates the uncertainty, while the full Bayesian posterior truly gives you large error bars in regions where you don't have training data. So to summarize, I talked about Bayesian fit of general parameterized MLIAPs, and hopefully convinced, as if you weren't convinced already, that noise assumptions are crucial. I demonstrated this method developed by us in the context of physical models, embedded model error model method, where statistical corrections are done inside the model, whether you inflate the parameters or do some changes in the model itself. That's sort of a secondary question. We reformulate inference of model parameters into a joint inference of model parameters and the model error correction. So this leads to a model-driven noise model, and it's meaningfully capturing the true residual. In linear regression models, we can do a few simplifications. We don't have to rely on uncertainty propagation machinery. We can just propagate it because it's linear exactly. Lots of challenges and choices to make in terms of priors, approximate likelihood, samplers, as well as where to embed. And you can think of it as a sort of diagnostic tool even, you know. I also connected this with variational inference. There's lots of similarities with embedded model error approach. Mechanically, they're very similar, perhaps different optimization method and also interpretation, right? Or what would we, how do we interpret this remaining statistical correction or this lift to probabilistic realm? How do we interpret that? In embedded model error, we may interpret it differently than in variational inference. However, I hope I brought the message home with variational inference that you have to use it with care, that it underestimates the uncertainty for over-parameterized models, which is often okay, but it's dangerous when extrapolating and certainly dangerous when one does active learning. So yeah, I'll stop here and thank you very much. I hope I stayed in time.
Thank you very much. Questions? Yes.
Thank you for the nice talk. You mentioned the challenges of choosing the priors, particularly for the embedding parameters in the model error that you're embedding. Can you say a little bit more about that and what kind of priors you end up choosing in those cases?
Did I understand correctly? The question is about priors?
Yes, particularly
okay.
For the embedding.
Yeah, so, well, we did the easiest approach, no prior or uniform prior on the embedding coefficients. Which is not always the right thing to do. I agree, but for now we are using just a uniform prior for both coefficient C and the embedding coefficient. But definitely the embedding coefficients here have sort of a spirit of sigma, right, of a noise. So some type of reference or Jeffreys type priors are probably better, and that would also regularize a little bit the posterior surface. But the examples I showed don't use that yet.
Then I think there's an online question.
Yes, hello, Khachik. This is Pascal Pernaud. I think a main issue with the embedded model is that when you do uncertainty propagation, the shape of your confidence bands or uncertainty bands is strongly determined by the analytical form of your model, by the Jacobian of your model according to the parameters. And for instance, for a linear model, we all know that the confidence bands for prediction has a diabolo shape, and that's something you cannot avoid. So if your errors are not the diabolo shaped, you would not get a reasonable error uncertainty bands. But I see that you were really careful about that. Do you have any prospects about how to mediate this effect?
Thanks, Dr. Pernaud. Nice to meet you online. We have been in touch over email too. So thank you. You are right. So this is fully sort of model-driven model error estimation, which you would think should take into account the DFT data as well to have uncertainty bounds that are more appropriate in general, right? So a remedy that I can suggest is perhaps join the external correction with internal correction. With proper regularization, it's possible that the external correction will sort of drive sort of the feed to the data in a better way, while internal correction deals with model internals. I'm very hand-wavy solution here, but we haven't done this. But in general, having both corrections inside and outside model can help this and can help disambiguate what's from model and what's not from the model. And there will be probably challenges in identifiability and how you choose priors to make this work, but at least it will give you a tool to sort of interpret what's coming from your model error and what's coming from your data noise. So, yeah.
Okay, thank you.
Thank you. Are there further questions, either online or here in the room? If not, let's thank the speaker once more.
Thank you.
You can see me fine, hear me fine, and see my slides.
Yes, everything is fine here. So
Perfect.
speak about community neural network potentials, control generalization errors, and enable active learning. Please go ahead.
All right. Yeah, thanks a lot. And before I start, I would like to thank the organizers, first of all, for inviting me, but also for trying to sort out all these audio problems during the whole course of the workshop. So thanks a lot for that. For those of you who don't know me, I'm currently working with Angelos Michaelides in Cambridge. And today, as already mentioned, I will kind of try to give you an overview of how we are using committee models to understand chemical processes. And in order to motivate why, what drives us and why we are using these models, to start with essentially showing you an application that we would like to understand. So this is water confined in complex environments, and this is highly relevant for a couple of really exciting applications like nanofiltrations, where you try to filter out certain ions by these type of nanochanels that I'm showing here on the top. You can also use these systems to do osmotic energy conversion and desalination, which I already mentioned. But if it comes to these systems, a lot of things are still unknown. So, for example, how water really flows through them and how reactivity is influenced by such a confinement regime. And questions like the material dependence and confinement effects are really still open, and we would like to address them based on simulations. However, if you want to treat these type of systems, you actually have to be very careful, and you can't really afford to make any errors. And in order to show that, I show you here a particular property of water on a graphene surface. So the contact angle of water and how it depends on the interaction strengths of a water molecule with this interface. As you can see here, just a small change of this interaction strength from 70 to 130 millieV completely changes the property of this droplet. It's either forming a very clear droplet or completely wets the surface. And that means if we want to understand these complex materials, we really need high accuracy, but at the same time also really large system sizes and long simulation times. And that means that essentially ab initio methods and force field methods can't really be used because of their certain advantages and disadvantages. And most of what we are trying is to utilize machine learning, as a lot of others here in the audience, to understand these type of processes. And so the particular machine learning that I'm usually applying is essentially the high-dimensional neural network potential approach by Jörg Behler, or introduced by Jörg Behler in 2007. And I will not really go into the details here, but it is very similar to all the other methods that we have seen already. In the first stage, you transform your structure into more meaningful representation. And then afterwards, you essentially use those inputs to predict atomic local energies to get the representation of the total energy. And maybe a side note here, so this formalism is not only in LEMS, but also in CP2K available and can be used. And usually we apply kind of an extension of that, a committee approach, which also a lot of you have already introduced. So I think I don't really have to go into details here. A lot of people have realized these advantages of committee models. First of all, you get a more accurate prediction. Then, most crucially, this estimation of an uncertainty, which you can then use for active learning purposes, as demonstrated here on the right. So you start with a potential energy surface and you just select some random points to train individual models, you will realize that like some of them might not be performing that well, but the average of them is actually a better predictor, and you can use the uncertainty estimation to really iteratively improve your prediction. And another side note that was also said already, like mentioned, I think by Michele in the very first talk, if you actually share your descriptors, I think Kars also mentioned that already, usually this is a very efficient approach, so very simple but powerful extension overall. And to give you an example of how we usually like use these committee models in order to like get a training set, I show you here an example of just liquid water at 300 Kelvin, the condensed phase setup, where we initially start just by selecting 20 random structures from an ab initio trajectory, and then we usually use the mean force disagreement to select new training data, add them in kind of batches of 10 per iteration, and train new models. And as type of like kind of properties over this like learning process, I show here in the top how the committee disagreement changes with adding more structures. And this is done for 3 different sets of structures. So in green, I show you what the training set disagreement looks like. Then in like other light green, the large pool of candidate structures that we actually filter, and then the selected ones which are actually like having large disagreement and should be added to the training set. As you see, this converges nicely on a log scale, and you essentially can truncate this after roughly taking 100 training structures. And the additional performance boost that the committee provides can be seen, for example, here in an out-of-sample validation set for the force errors, where like if you only take one committee member, so a single model, you really like have large errors, and like the largest or best performance boost is actually very small data sets. But even if you reach essentially 100 training points, there's still an additional benefit of like forming this committee in the overall performance of the model. And this has also been shown already, so I will go over this rather quickly. The committee disagreement allows you also to really selectively look at the weaknesses of your models. So for example, here done for this model that I've just shown you in the previous slide, applied in a situation that hasn't been seen before, the water-air interface. And as you would expect for a model that only really knows condensed phase structures, you really have like a large disagreement at the very boundary to the air interface. And this can then really be utilized to like actively select new structures. Something that is probably like connects nicely to Kars' talk of earlier today is an idea that we have been using in order to control the stability of such committee models. It's essentially the opposite as like done in hyperactive learning. You can essentially realize that small disagreement means you have a stable and accurate model, and you can use that in order to define a simple biasing potential that acts on your energy disagreement. And the way we understand that is essentially it is like erecting a barrier around the area of your training data where you have small errors, and like the sketch should kind of motivate what I mean here. So in feature space, you have your training data, which should usually have low error estimates, and you erect an effective barrier preventing the simulation to drift into like 2 unknown regions. And we apply this error, this harmonic term, which is essentially shifted to slightly larger disagreements, to the energy on purpose. First of all, because it's simple, like as Kars has also mentioned, you can very easily derive the forces acting on the atoms. But on top of that, it's also a relatively mild perturbation of the system. And so here in the middle panel, I show you essentially how this harmonic potential looks like. So it's just harmonic potential shifted to whatever energy disagreement you want. And where an unbiased distribution of the energy disagreement would look like the green curve, you can really then push back your disagreement to essentially low values. But at the same time, if you look at something like the force disagreement, this is essentially a really, really small bias on this. So there, you only really feel like mild influence on the forces, which means like your local environments are not really perturbed that much. It's really like global rearrangements of the system that are prevented by this biasing. And with that, I would like to essentially like switch to more or less application scenario, or like how these ideas can be used in order to get to the rapid development of MLPs for complex systems. And like all these features, the error control and the active learning used in committee models actually allow you to build an end-to-end framework for these complex systems in a simple manner. And that's what has been recently published by us in PNAS. And our conceptual idea here is that instead of building a globally optimal model, like a lot of others of you have done, we would rather just concentrate on a specific thermodynamic condition and make the development of the model as simple as possible. And this still allows you usually to answer a lot of scientific questions where like this thermodynamic condition is just relevant for what you would like to understand. And at the same time, we then remove as much user input as possible and build essentially an end-to-end pipeline in an automated fashion. And another idea there is, of course, that we make all code available, so or like either build on open source code or make the code available so that it's just an end-to-end framework. And our idea there looks like this. It's essentially organized in a two-step or three-step process. First, we explore the system of interest with a very short ab initio MD of the system size that is relevant to capture all local environments. And that is then essentially filtered by active learning to build a committee model in essentially one step. And in the next step, you can then apply this model and validate it, of course, for larger system sizes and longer simulation time. To give you an idea, usually for the systems we are looking at, this like 30 picoseconds is sufficient to generate the models. And what types of systems have we benchmarked with this framework? So this is what we have concentrated on: ions in bulk solution in water, water in carbon and HBN nanotubes, water under MOS2 confinement, and water at the titanium dioxide surface. And for all these like different systems, we have essentially built these committee models by identifying just something like 300 structures from relatively short ab initio simulation. And this is essentially crucial, the low number of structures, if you would like to upgrade your electronic structure setup to something much more expensive, like RPA or yeah, even the hybrid function can be quite expensive for the system sizes that are relevant here. And another crucial aspect of such a development is, of course, that you need to validate these models somehow. And like for 6 different models and different systems, that can become tricky, of course. So we have tried essentially to come up with like an automated fitting validation procedure, which concentrates on 3 crucial properties: structural, dynamical, and essentially machine learning properties, where structure is captured by the radial distribution function. The dynamical properties are like captured by the vibrational density of states, and the forces by, or the machine learning aspect by the force are missing. And we essentially reduce all these different properties shown here on the right for one of these systems, the fluoride ion in water, into a score, so that you can compare them between the like compare the performance between the different models. And so that allows you essentially, once you develop a new model, to get a score and compare it to previously established ones and properly tested ones. And we have, of course, also made sure that other properties are well captured by these models, like hydrogen bonding, the density profiles, or water orientation. And essentially for these 6 systems we have picked, we more or less get very similar scores, which should give you an idea that the quality of the models is comparable. And yeah, so this brings me essentially to the first summary of my talk. I've essentially shown you this end-to-end framework where machine learning can be used to generate simple models for complex systems and in order to get insight. And in the next part, I will essentially show you how that framework can be used for the understanding of monolayer confined water. But before I go there, are there any immediate questions? So I usually like pausing in the middle of the talk before questions are lost. If that's not the case, I will just continue.
Can I ask a question?
Sure.
I was wondering, so once you use your committee approach to sort of do the active learning, then arrive at a final model, that model you use for large-scale simulations, that's a single model, or is it also possible to use a committee for a large-scale simulation to gain access to some sort of disagreement on predictions?
Yeah, no, so
large scale.
The whole, like every model that I'm using is essentially a committee model. So also the application is done with the committee, and you have access to the error estimate on the fly. And the biasing, for example, you can also utilize that in cases you want, but usually you don't want that for production runs, rather like to explore other phase points. Okay.
Yeah, thanks.
Doesn't look like there are other questions, so I will just continue with this application to monolayer water. So briefly to motivate why we're interested in this particular system, there has been really a lot of experimental work on understanding modular or like confined water, going to the extreme confinement regime where you end up with just a single layer of water confined by some material. And that has, for example, led to the measurement of very low dielectric constant of water, but also the possibility of the existence of a square phase of ice. And like all these, like I could name many more papers here in this experimental work in this direction. All these really point towards remarkable different properties of nanoscale water compared to bulk phase. And we would like essentially to build a molecular level understanding as a foundation for technological application. And in order to do so, we essentially use the methodology I showed you before to develop a machine learning model, which was essentially guided by quantum Monte Carlo. So this is, of course, another aspect that was mentioned multiple times already. You not only need to control the errors of your model, but also of your underlying reference calculation somehow. And we utilize quantum Monte Carlo calculations for relevant phases of monolayer water in order to select a relevant or a good performing DFT function. And that benchmark essentially allowed us to select RefPBE0 with a dispersion correction, like hybrid functional with a dispersion correction. It's a very, very good DFT function for the description of confined water. And then we have essentially utilized an adaptive improvement of the model, so like in multiple stages, exploring new points of phase space and then doing active learning, improving the model. And we essentially started out with this liquid water model that I briefly mentioned in the beginning, and really pushed that like to these confinement regimes where we just study a single layer of water in this adaptive manner. And the actual simulations that we ran in the end is like this single layer of water confined by a Leonard-Jones potential, which has been fitted to reproduce carbon water interaction energies based on quantum Monte Carlo data again. And then what we do is we essentially like study the behavior of this single layer of water as a function of pressure and temperature, and the pressure is applied essentially lateral to this monolayer in order to mimic the pressure that it is exerted by graphene walls that are kind of closing at the ends and then like exerting this pressure on the water. And usually we study something like 144 molecules per unit cell. And then the simulation techniques in order to arrive at the phase behavior of this monolayer water is we do random structure search to find stable ordered phases. And then afterwards, we do thermodynamic integration, compute free energies. And in the next step, once we have the relative ranking of all the phases, we also ran coexistence simulations to locate the solid liquid boundaries. And that essentially like led to this phase diagram that I'm showing here, which might be relatively confusing at first, but so let me walk you through this. What I'm showing here is essentially the stability of, or like the most stable phases as a function of temperature and pressure, where at low temperatures, we essentially have all the ordered phases, and we recover really rich phase behavior. They are already at low temperatures. from hexagonal over pentagonal to square and flat rhombic phases. Once you go to like higher pressures, you essentially move to more compact phases of this monolayer water. And then on top of that, we actually see very, very interesting melting behavior to the liquid, where first the hexagonal phase just melts as known essentially from bulk to just the liquid state. But we then arrive at essentially the first triple point with the pentagonal phase. And further on, we have another triple point with the flat rhombic and pentagonal phase. And all these have been essentially validated with coexistence simulations. But what is really more interesting is the corner top right here. What happens at relatively high pressure, so something like 2 gigapascal, sorry, and 300 Kelvin and onwards. So there we actually find a so-called hexatic phase, which is neither a liquid nor a solid. It's a phase that is known from 2D materials, like modeled materials, but we also find it here for water. And if you exert even more pressure, you actually dissociate the water, and you arrive at the situation of a superionic phase. And I will, in the next slides, go into a little bit more detail what these phases look like. So this hexatic phase is essentially a phase that has no translational long-range order, because like dislocations are there and like are propagating through the system. And in order to show that, I have a short video here to show how this phase looks like. And there is no long-range translational order, but there is hexagonal orientational short-range order, which is the kind of hallmark of this hexatic phase. And it's essentially triggered by rotations of the water molecules, which is very reminiscent of the free rotor phase of hydrogen. And of course, we also validated that this phase is actually like meaningful under explicit confinement. So we also have simulations where we included the carbon atoms, and we really recover the same phase behavior as for our larger scale and longer simulations with Lennard-Jones confinement potential. And then the other interesting phase is the superionic phase. And to briefly explain what I mean with superionic, so the phase superionic is essentially like comes due to dissociation of water, and the first property relevant for that that I'm showing you here as a function of temperature is the dissociation of an OH in 100 picoseconds. And you see that once you increase the pressure, this really like goes up quite a lot due to the compression of your lattice, and you arrive at a situation where at 600 Kelvin in 100 picoseconds, 30% of your OH bonds are dissociated, so highly dissociated state. And we also computed the ionic conductivity of this at this pressure as a function of temperature. And you reach essentially a cutoff that is usually used for superionic behavior, something like 400 Kelvin and onwards. The ionic conductivity gets even larger. And the phase, like what it looks like is essentially you have a fixed lattice of oxygen atoms in hexagonal arrangement, and then like diffusing hydrogens due to like constant breaking and formation of OH bonds. And to again show you also a video of that, here on the left, I have essentially highlighted 4 oxygen atoms which remain fixed in the process of the simulation, and then 4 hydrogen atoms in yellow which diffuse or like are transferred through the bonds. And again, also here we made sure that this behavior is also recovered if we actually have explicit confining materials. So also there we do see essentially the same behavior of like very easy fast photon transfer. And the interesting fact is, or the interesting finding here is that this phase is found for much lower temperatures and pressures than usually expected in bulk phases. So I think the recently found bulk superionic phase of water only really appears at something like 60 or 50 gigapascal and 600 Kelvin. And this brings me to the last summary of my talk. So I'm just showing you again this phase diagram that we have essentially determined with these 2 unique phases, the superionic behavior at high pressures and temperatures, and this intermediate phase of hexatic nature. And all this is essentially enabled by error control via community neural network catches. And with that, I'm at my last slide. Let me just thank my collaborators, in particular Angelos, Michaelides, Venkat Kapil, and Andre Mazalek, who were like really instrumental in like these results that I've shown now. And with that, hope I'm not over time, and I'm looking forward to any remaining questions.
Are there any questions? So maybe starting here. So you have error bars. So sometimes they're horizontal and sometimes they're vertical. What's behind this? Is this like the way you do the continuation, or?
Yeah, so all the horizontal error bars are determined based on coexistence simulations. And this is essentially the resolution that we have in our temperature grid. So this is how we determine those. Whereas the error bars here come from the free energy calculations, which we performed in order to determine them.
Okay. Are there any, thank you. Are there any other questions? So regarding the first part,
yes,
a very clear strategy how to tackle this problem. Is there anything I couldn't figure out with my limited expertise, but is there anything related to water that you do in the way you do the committee models, etc.? It sounded like a generic approach, and I wonder whether it was something specific to water that I missed.
No, not really. So this pipeline should work for also other systems. We just decided to concentrate on the subclass because it is usually like relevant enough on its own. But like we also looked at other systems. Definitely, it's just kind of our flavor of what Angelos Michaelides group is doing. Like we just like water a lot, so that's why we study it a lot.
I also like water, but mostly implicit one. But anyway, okay. Well, thank you. Is there any other question online? I don't see. Here, yes.
Hi, Christoph. Can I just quickly ask how long your total time running the active learning before you have something which you then use in simulation, including all the DFTs there?
How long the whole development takes, or like how long the simulations are as like simulation time?
So if you were to like start from nowadays and start your active learning, how long do you reckon it is in total before you have something that you can start using?
So usually the limiting step is really not the active learning, but the ab initio MD, and also those can be done pretty fast depending on the system you're studying. But I would say like a decent first model we can get in something like 2-3 days up to a week. Of course, then it is like as you all know in the details, right? What you really want to look at, but it is a rather fast pipeline. So the systems I've shown you here were all essentially done with the same set of parameters in a couple of days.
Okay, thanks.
Any other question? If no, we thank Christoph once again. And I think it's appropriate here at this point to thank, in the names of all of the participants, to thank the organizers for putting together this nice workshop, the social dinner that was very enjoyable for those who were here, and also the upcoming boat trip tomorrow. So thank you very much. I guess it's not exaggerated to have a special thank to Michael, who seemed to have done a lot of work. So thank you, Michael.
All the
Let's meet at 9:20 at the workshop. That's my final answer. Thanks for being here.
But at Ushi.
At Ushi. Yeah, 9:20 at Ushi.
Okay, so thank you for attending online.